Network covalent atomic solids. So carbon makes several different types of network covalent solids. There's several different forms. These are called allotropes. Different forms of the same element. One example is graphite. So in graphite, the carbon atoms are covalently bonded to each other in these six-membered rings, and we have this two-dimensional sheet, this flat sheet of these hexagonal rings, and then we have layered on that other sheets, and what's holding the sheets together is just dispersion forces. And because of this, the layers can slide past each other, and that's what makes graphite slippery. Right? So you can use it in a pencil. It's a pencil lead. Pencils have no lead in them. It's graphite. And as you drag your pencil across the paper, pieces of the graphite are going to slide off and stick to the paper. It can also be used as a lubricant. You can actually take your pencil, like if you have a key that's not going in very well, you can take the graphite on your pencil and scribble all over the key, and that might lubricate it enough to get it to go into the lock and work again. Graphite's a good electrical conductor because there is an extended pi bonding network above and below these sheets. And that's kind of going back to the valence bond theory that we talked about in molecular orbitals. So graphite has a density of 2.2 grams per cubic centimeter. If you take the graphite and you put extreme amounts of pressure on it, like 50,000 atmospheres, and you heat it up pretty high too, you can cause those carbon atoms to rearrange and form a more dense substance that we know as a diamond. So diamonds can be formed naturally, deep underground. That's why people have diamond mines, and they dig them up out of the ground. But they can also be made synthetically. So in the diamond, now we have the same carbon atoms, but now instead of in layers, they are bonded in all three dimensions. The unit cell here for the carbon atoms is very similar to that zinc blende structure. But instead of these being attracted by ionic bonds, each of these atoms is covalently bonded to 4 other atoms. Diamond has a melting point of about 3,800 degrees, extremely high. It's very hard. It's an excellent heat conductor, and this makes it really useful for abrasives and cutting tools because it's going to be hard, so it's not going to wear down, but it'll also transfer the heat generated by that friction into the blade so that you don't burn your wood as you're cutting it. Back in the 1980s, they discovered a new form of carbon. These are called fullerenes or buckyballs. This is Buckminster fullerene. It is a soccer ball-shaped cluster of 60 carbon atoms. And so the carbon atoms here are bonded in, there's hexagons and there's pentagons. And it makes this ball structure. And so you can have ones that are different sizes. They can be as small as 36 carbon atoms to over 100 carbon atoms. Kind of crazy. And then we can also synthesize these carbon structures called nanotubes. So this is essentially graphene, which looks a lot like chicken wire, right? It's these hexagons. You can take the graphene and you can roll it and make it into a tube, right? So that's called a nanotube because it's really small. You can have one that's just got a single wall, or you can have a bunch of them nested inside of each other, a multi-walled nanotube. Those nanotubes are 100 times stronger than steel and only 1/16 as dense. And so they're really useful in applications where you want something that's very strong but also very light. So golf clubs and bicycles will often also say, well, it has a graphite frame. Why do I want a bike with pencil lead for a frame? That's not a good idea. Well, it's not pencil lead. It's really graphene in nanotubes. It's really cool. You can also use these nanotubes as really, really tiny wires because they conduct electricity. Another type of network covalent atomic solids are silicates. So these are a little bit different in that there's two different elements in here. There's silicon and oxygen. But again, the atoms are covalently bonded to each other. So these are common in ceramics and cement and glass. Think sand, right? Quartz is a form of silica. So silicates make up about 90% of the Earth's crust. Silicon and carbon bonded together. So silica has a formula unit of SiO2, but it's not an SiO2 molecule. That's just the lowest ratio. For every silicon atom, there are 2 oxygen atoms, and they're bonded together in this way. And then the chapter goes on and talks about different types of silicates and ceramics and the differences between those. And some of them have different elements in them, and that affects their properties. Cement and concrete. Glass. Glass is a form of silica, and there's a whole bunch of different kinds of glass with different properties. Come on. And then if you're interested, this section talks about semiconductors. How do semiconductors work? If you're interested, you can read this. Band theory is really cool, but it's not in the course outline of record, so we're not going to go over it in detail. But it's in there for you to read about. And the last section is about polymers and plastics. And polymers have repeating units called monomers that are stuck together in long chains. And these can have branches, they can have really long chains or shorter chains, and all of those different variations affect the properties. So we get things like plastics, there's different kinds of plastics, but there are also natural polymers like cellulose. And that is the end.